Good afternoon. I'm Denis Dondi. I'm a third-year PhD student, and I'm here to present you my research activity on wireless sensor network for industrial application, and in particular the research on solar energy harvesting circuits for wireless sensor network nodes. During last year, a huge interest on wireless sensor network has leads researchers to develop even more intelligent and power-consuming wireless devices. Nowadays, researchers are facing the problem that these wireless devices has a very low battery lifetime. So to overcome this drawback on the power hungriness, possible solution could be the implementation of ultra-low power architectures, the adoption of power-saving algorithms and protocols, or the possibility to collect energy from the ambient, in particular with energy harvesting systems. So the energy harvester that we have in our mind is a circuit that collects energy from the sun with a solar panel. Then a circuit collects this energy and store it into an energy buffer that could be a battery or a supercapacitor. And then the CDC switching regulator generates the voltage to provide the power supply to the wireless sensor network node. So first step in the development of an energy harvesting system, it's the knowledge of the amount of power available at the source. So since the solar panel manufacturer provide very few information about the behavior of their products, we have implemented a model, a SPICE-like model of the photovoltaic panel to predict the amount of power available at the output for a very wide range of working conditions that depends on the incident sunlight and the working temperature. The photovoltaic panel model is composed of a connection in series and parallel of photovoltaic cells that are represented in the picture by the schematics and described by the equation in the bottom. The model has been developed and verified by the measurements of a real commercial photovoltaic panel. Once the model has been verified, we change our interest on the analysis of the solar harvester. In particular, the solar harvester can be, it's composed by three main blocks. At the CDC input stage that generate the charging current for the energy buffer, that in our case is a supercapacitor of 50 farad. Another important block is the maximum power point tracker. This circuit estimates the optimum working condition for the photovoltaic panel by sensing the incident light from the sun. And the last block is an output DC-DC switching regulator that generates the output supply for the wireless sensor network node. The analysis shows that to improve the performance of the harvester, we have to optimize the main block that is the DC-DC input stage. So in order to estimate the behavior of the circuit, we have implemented a model of the DC-DC input stage that is described by an analytical equation in both the on state and the off state of the circuit. The estimation of the behavior through the analytical equations lead to calculate the power losses of the circuit during both the on state and the off state. These power losses are conduction losses of the passive components and switching losses of the active components, such as the MOSFETs and the diodes. In addition, with the photovoltaic panel model, we can estimate the input power, and these quantities are lead to estimate the efficiency of the solar harvesting system. And on the bottom, we can see the comparison of the efficiency extracted from the simulation of several different implementations of the circuit with different input capacitor and different inductors. Finally, to validate the the modelization of the photovoltaic panel and the circuit, we have implemented a solar harvester prototype with commercial components. In particular, values of components are the one highlighted from our analysis. And the prototype leads to reduce the average current that is the main aspect for the conduction losses, and to maximize the transmission frequency that is lead to a very high efficiency. The prototype has been measured under different light conditions. In particular, this is the result of the measurement with an incident light of 800 watt over square meter. That is the typical light intensity of a spring sunny day. And the maximum efficiency obtained is 81%. That is only 4 percentage points under the estimation from the simulation. These results confirm that the modelization and the proposed design methodology are very good to predict the amount of power that we can extract from the ambient to power up the wireless sensor node.